A blessed time to everyone. I'm Mark Miragan, a team leader in Team 9 with my fellow teammates in Module 9, Computer Systems, Organization, and Architecture. And here's a schematic of our overview.
An overview of our module explores the differences between computer organization and computer architecture on how a computer builds on the inside and works from outside. Now let's begin the introduction of computer organization and computer architecture. And before that, let me criticize the understanding of hardware and software differences. A component of hardware and software. Hardware is a physical part of computer like CPU, memory, hard drive, keyboard, and monitor, while software is a set of commands or programs that tells the hardware that do what they don't, like Windows, Mac OS, Linux, apps, games, and etc. Both software and hardware are important because a computer will not work properly if either one is weak. Like if the hardware is powerful but the software is poorly designed, the computer will be slow. A main goal of computer organization and architecture is to reduce the execution time and better performance that all integration both software and hardware runs efficiently. And here are the differences of computer organization and computer architecture. Organization is like a software or programmer's view on how it's worked from outside, while architecture is a hardware or engineer's view or on how is it built inside. In summary, organization is about the inside process of the computer, while architecture is about the plan or design of the computer. In computer architecture is a logical design that allows us to write to run commands, instruction sets, data types, input or output, and memory addressing that needs function. And in computer organization is a physical designs that concerns on interaction on components that focuses on how architecture is actually implemented in hardware.
A blessed time to everyone. I'm Sandra Mamunti. I will be presenting to the attributes of computer organization and computer architecture.
Computer organization. Learn a CPU, memory, and inputs and outputs device, focusing on how they interact to execute instructions. It explains each unit's function and system operation in keeping low-level hardware detail hidden from programmers. Attributes of computer organization. Control signals are electrical light pulses that guide the timing and coordination of computer operations, ensuring that data and commands move smoothly through the system. Example: a traffic light telling each component which when when to go, stop, or wait. Under the attribute of computer organization, aside from control signal, there are other important components includes the computer peripheral interface and memory, and all of them has a role to function system effectively. Computer peripheral interface. Peripheral is the device connected to a computer like a printer or mouse. It is not part of the main system but adds extra functions and often depends on the computer to work. Interface is the point where a computer and a device interact. Some interface, like touchscreens, sends and receive data, while others, like a mouse or microphone, only send data. A computer peripheral interface is a bridge between computer and device. It has two types: hardware, which links physical parts like buses and I/O, and software, like links programs with hardware such as OS and printer. In interface, there are two types: software interface and hardware interface. Software interface refers to a range of different types of interface at different levels and operating system that interface with piece of hardware. Hardware interface exists in computing system between any of the components such as various buses, storage device. The last one under computer organization is memory. Memory is the collection of storage units or device together. Example is like a computer notebook storage notes. A second, what is a computer architecture? Computer architecture is a blueprint and theory of how a computer is designed, how it behaves, and how software and hardware interact to form a complete system. Under the computer architecture, there are other definitions. Baer. Architecture designs an integrated system on programmers can use effectively. Hess. It, it is the study of a computer's structures, behavior, and design. Ag-ala. It defines system design at both full system and subsystem levels. Foster. It is the art of designing a user-friendly and efficient machine. Hennessy and Patterson. It serves a interface between hardware and low-level software. Those other definitions are different experts explain computer architecture from different angles. Programmers view, system design view, usability view, or hardware software interaction view. That's why they are all grouped under computer architecture that all are different perspectives but they describes the same concept. Therefore, computer architecture refers to attributes of a system visible to programmers. Because programmers have direct use on instruction sets, data type, and addressing modes that commands and control they have over the system. Attributes that have a direct impact on the execution of programs. And lastly, here are the attributes of computer architecture. Attribute of computer architecture, instruction set architecture, the part of processor that are visible to a programmer to compiler writer serves as a boundary between software and hardware. Data representation refers to a method used internally to represent information stored in a computer. Computers store lots of different types of information, numbers and text. I/O mechanism, the communication between an information processing system. Addressing techniques are the aspect of the instruction set architecture in most central processing unit designs. Overall, computer organization explains how components operate and connect, while computer architecture defines the design and interaction with software. Together, they describe the system's function, structure, and performance.
A blessed time to everyone. My name is Precious Jewel Cabocana, and I will be presenting the structure and functions of computer system.
And there are components under structure and function in computer. A computer is a complex system that can be understood as a hierarchy of each subsystem is divided until to reach the lowest level of components. Examples of computer structure and function. Computer system highest level, the whole PC or laptop. Subsystem, CPU, memory, input, output. Inside the CPU, control unit, arithmetic logic unit, ALU, register. Inside the ALU, logic gates and or NOT. Inside logic gates, lowest level transistor. And what is the difference of structure and function? Differences of structure and function. Structure is an arrangement of components and their interconnections. Example, how CPU, RAM, storage, and I/O are arranged and connected, while the function, the role and operation of each component. Example, what each does: CPU processes, RAM stores, storage saves data, and there's There are basic computer function. Basic computer function. Data processing. That computer collects raw data and manipulates it to produce meaningful information. Data storage. The computer keeps data for future use, either short-term in memory or long-term in storage device like hard drives, SSDs, and flash drives. Data movement. A computer communication with the external environmental through peripherals, keyboards, monitors, printers, and data communication network. Control oversees and coordinates data processing, storage, and movement, ensuring operation run in the correct order and resources are used efficiently. A computer is a hierarchy of subsystems where structure arrange components and function defines their rules. Its four basic function processing, storage, movement, and control. Explain how it operates from the smallest transistor to the whole system.
Good day everyone, I am Zyrene Corpus and I'm going to present functional view of the von Neumann model. The von Neumann model is the foundation of the modern computers, built on five main parts: input, output, memory, and the arithmetic logic unit, and the control unit. It explains how data is entered, stored, processed, managed, and then delivered as output, making it the basic framework for computer operation. Input, getting information into the computer. Example, keyboard and mouse. Output, getting information out of the computer. Example, printer and monitor. Arithmetic logic unit, a unit in a computer which carries out arithmetic and logical operations. Memory, storage of information. Control unit, make sure that all the other parts perform their task correctly and at the correct time. The system bus model is an improved version of the von Neumann model. Instead of each part connecting directly, the CPU, memory, and input-output communicates through a common pathway called the system bus, which is divided into the data bus, address bus, control bus, and power bus. Some systems even add a separate input and output bus for faster device communication. Data bus carries the data. Address bus tells the location of data. Control bus manages and coordinates operations. The system bus components. Data bus transfers the actual data between CPU, memory, and devices. Address bus carries a location in memory or device where data must go or come from. Control bus sends signals from the CPU to coordinate actions, read, write, timing. Peripheral input and output bus connects external devices, example USB and PCI, directly to the CPU.
Hi everyone, I am Krisha Perez and I presenting the motherboard.
Motherboard: a printed circuit board containing the principal components of computer or other device, with connectors into which other circuits ports can be slot.
In another word, a motherboard is the main foundation of a computer. It is like the body's central nervous system and holding the CPU, memory, and other essential parts while providing slot and pathway that let components communicate and work together as one machine. Motherboard components and subsystem.
Northbridge is controller chip linking the CPU with RAM graphics, AGP, PSI Express through the frontside bus. FBS enable fast data flow, vital and system performance. Southbridge is the companion chip, the Northbridge in the motherboard chipset. It handles slower components and peripherals, managing input, output, storage, USB, audio, and legacy device. System bus is the main pathway of cable and connector linking the CPU with main memory and relata. Omnibus, it serves as the communication system between components. System bus link the CPU with main memory and sometimes the L2 cache. Other buses like I/O buses branch from it to connect the CPU with peripherals. It's combined their main buses. Control bus sends control timing and coordination signal managing data processing. Address bus specifies memory location for data reside where data goes. Data bus, the directional path carrying actual data between CPU, memory, peripherals. Those are the additional depth meaning of system bus that includes there a motherboard diagram. And here is a schematic of motherboard diagram. Number 1, CPU is the brain of computer that are connected to Northbridge called frontside bus. Number 2, a clock generator ensure all data transfer happen in synchronized rhythm. Number 3, a Northbridge and Southbridge are internally bus and called chipset. Number 4, memory bus connected CPU to RAM memory slot. Number 4, memory bus connect CPU to RAM memory slot. Number 5, graphic bus connected CPU graphic card slot, AGP, PCIe. Number 6, a Southbridge, a chip that manage legacy and low-speed device that connected to Southbridge via LPC, bus low pin, count bus. Number 7, expression slot, PCI Express, Northbridge high speed, PCIe, slot Southbridge, slower PCI slot.
Blessed time to everyone. I'm Mardi Bakay and I will presenting a digital components. And digital components consist of transistors, microelectronics, and levels of integration. First one is transistors. Replace vacuum tubes. Smaller, cheaper, less heat dissipation, solid state device, made from silicon sand. Invented in 1947 at Bell Labs. William Shockley. High-level digital circuits are built using group of logic gates called components, rather of individual logic gates. One example is the majority function, which works as a component. Hierarchy. Transistors, logic gates, components, majority function, complex digital circuit, digital system, CPU, memory devices. A high-level digital circuits exist to make engineers mix design assure that gates are grouped into components like others, multiplexers, and if only on individual logic gates only. The circuits would be extremely complex to manage. Hierarchy. This is the digital design hierarchy showing how transistors form gates, gates from components, components from circuits, and circuits from complete digital system. 1. Transistors are the basic building blocks of digital electronics, acting as tiny switches that control the flow of electricity. 2. Move to logic gates. In combining transistors, must create logic gates such as AND or AND NOT, which perform simple logical operations. 3. Next is components, rather connecting individual logic gates directly. High-level digital circuit design group multiple gates into components, which perform more complex function than individual logic gates. And here are example of image of gates. First one, this is the logic gates. And 2, logic gate schematic. And next is microelectronics. Microelectronics, literally smaller electronics. And a computer is made up of gates, memory cells, and interconnections. This can be manufactured on a semiconductor, silicon wafer. This is the image of microelectronics manufactured on semiconductor. And next, we have levels of integration. Levels of integration, number of gates in an integrated circuit or IC. Smaller scale integration or SSI, 10 to 100 gates. Medium scale integration or MSI, 100 to 1000 gates. Very large scale integration or VLSI, 10,000 upward. Large scale integration, LSI, 1000 to 10,000. Level of integration breakdown. 1. Small scale integration or SSI, gate count, 10 to 100 gates. Complexity, very simple. Examples, basic logic gates, flip-flops. 2. Medium scale integration or MSI, gate count, 100 to 1000 gates. Complexity, small functional blocks. Examples, adders, multiplexers, decoders, counters. Number 3. Large-scale integration or LSI. Gate count 1000 to 10,000 gates. Complexity, more complex circuits. Examples, simple processor, memory chips, RAM, calculator chips. Number 4. Very large-scale integration or VLSI. Gate count, 10,000 gates and upward. Complexity, very advanced. Examples, microprocessor, advanced memory chips, modern CPU, and GPU. These levels are approximate, but the distinctions are useful in comparing the relative complexity of circuits. And next are the scientific prefixes. There are smaller than 1 and larger than 1. For computer memory, 1K equals 2 to power 10 equals 1024. For everything else, like clock speeds, 1K equals 1000. And likewise for 1M, 1G, etc. Those are all components under of digital components.
A blessed time to everyone. I am Paul Bautista and I will representing data representation. What is data representation? Data representation is a common data to utilize in all times many forms, like letters of the alphabet, A to Z, numerals, 0 to 9, symbols, at, and asterisk, and control keys, shift, control, and enter. These are things that humans easily recognize and work on keyboards. Data is convenient for human and being, but all in data is digital computer represented in binary forms. Humans see letters, numbers, and symbols, but computers cannot. Computer only understand binary from zeros to ones. Every letters, symbols, and numbers is translated into binary form so that the computer can process it. Some coding systems are used to represent this data into binary forms. Characters are represented by sequence of bits. A coding system like a dictionary that matches human readable characters in their binary values. Example, the letter A in ASCII is 01000001 binary. The number 5 in BCD is 0101 binary. So, each character is stored as a sequence of bits. Bits are just zeros and ones. That's how computers represent in process in types of information. And these are famous coding system that been used for data representation. First, what is ASCII? ASCII is American Standard Code for Information Interchange. ASCII is one of the oldest and most important coding system that each alphabetics, numerals, and symbols are own binaries the computer can understand it. ASCII uses 7 bits for each character. 7 bits means 2 raised to 7 is equal to 128 possible combinations. So ASCII can represent 128 different characters. In binary number, a string of 7 zeros and 1. Example, 7 zeros, 0 in decimal, NUL control code. 1 0 0 0 0 1 65 in decimal, capital letter A. 1 1 0 0 0 0 0 1 97 in decimal, small letter A. Meaning, a 0 and 1 can be more digits of 8 bits. In some system, an extra 8-bit is used to error checking in terms of data and transmitted by accident changes of binaries can be set a 0, a parity bit. Example, if one binary digits flip due the transmission error, the parity can reveal the mistakes. Character A. Character A. In decimal, 65. In hexadecimal, 41. In binary, 01000001. Therefore, a computer processes of stores in a letter A. Next, what is EBCDIC? EBCDIC is Extended Binary Coded Decimal Interchange Code. A EBCDIC is a binary code alphabetic and numeric that IBM developed on large OS. It pronounced EB, C, Dick, or EBCDIC. EBCDIC uses 7 bits. So, sa ASCII, ang ginagamit ay 7 bits lang. Dito sa EBCDIC is 8 bits. 8 bits for each character, 1 byte. 8 bits means 2 raised to 8 is equals to 256 possible combination. A comparison of ASCII and EBCDIC. ASCII, 7 bits is equals to 128 character. In EBCDIC, 8 bits is equals to 256 character. In binaries of character A, ASCII is 01000001. In decimal, 65. In hexadecimal, 41. In EBCDIC, 11000001. In decimal, 193. In hexadecimal is C1. Even though both coded as a capital letter A in binary representation is a different. Next, what is BCD? BCD. BCD is binary coded decimal. A BCD is representing decimal numbers in binary. Each decimal digits 0 to 9 are valid in written using 4 bits. 1, 2, 3, 4 bits. Example 1. 3D is equals to 0011B and 9D is equals to 100B. Okay, example 1, 3D. 3D, D is digits. 3 digits is equals to 0011B. The B is binary. So, call 3 digits is equals to 0011 binary. And next, 9 digits is equals to 1001 binary. Highest decimal number were coded to BCD is 9. 9 is equals to 1001. Binary in 4 digits. Utilized in decimal. 0100 4. 0011 3. And 1001 is 9. Example 2 is a 43D. 43D is a 43 digits. So, encode the number 43. 43D is equals to 1, 0100 is a 4. And the 3 is 0011. Yun yung 3. 43D is may apat na 4 digits. So, sa 4 is 0100, 4 siya. So, sa 3 is 0011, 3. Saka 43. To encode the number 43, 43D is 0100, 1001. So, siya ay 43. Data representation is all about converting human readable character into binary codes using standards like ASCII, EBCDIC, and BCD.
And hi again, I'm about to endpoint the lesson around number systems at the last. And now, what is number system? A number system is a fundamental of representing numbers using a set of symbols defined by its base or radix. Understanding number system is fundamental because computers use them to store and communicate data, meaning to be it's a computer language communication. And there are 4 kinds of number system. First, decimal system. It is a number system humans use in everyday life for counting and calculations. It is based on 10 unique symbols called Arabic numerals from 0 to 9. Because it has 10 digits, its base or radix is 10, meaning each place value is increases by powers of 10. And next are binary system. A binary system is a fundamental language of digital computers. It works using only 2 states, such as on or off or true or false, which are represented by the symbols 0 and 1. Its base is 2, and each digit in binary is called a bit, short for binary digit. And next are octal system. An octal system is a shorthand way of writing binary numbers more compactly. In this system, every group of 3 binary digits is replaced by a single octal digit, which makes numbers shorter and easier to read. It uses 8 symbols from 0 to 7 and has a base of 8. And last, our hexadecimal system. A hexadecimal system most compact way of representing binary values. It combines 10 numbers from 0 to 9 with 6 letters A to F. that an A to F is represent the decimal values on 10, 15, and this gives a total of 16 symbols, that making its base of 16 because each hexadecimal digits are corresponds to 4 binary digits and is widely used to simplify long binary numbers in computing. To make this all clear, here are the table of number system.
To make it all clear, here are the table of number systems. And now a process computation of number systems. In here are number system to determine the n value to recognize if it is decimal, binary, octal, and hexadecimal. And all n values are no limitation, can be up from 0 to infinity. In those tables are on how to find and compute a decimal into binary, octal, and hexadecimal. If a decimal is given, then to compute its missing binaries, octal, and hexadecimal. Example, a decimal 74 in calculation to find its binary, octal, and hexadecimal. In any numbers of decimal, in binary, always divide 2, and in octal, divide 8, and in hexadecimal, divide 16, until getting the least dividend of all the results and combine all the remainders upward to get its overall computation. In reverse, now a decimal is missing, but the binaries, octal, and hexadecimal is given. Here are the calculation to retrieve a decimal. In this example, here first, binary to decimal. As you can see, that binary is listed upward reading in first column below. And after each numerals of binary must be multiplied by base of 2 with an increasing exponential. And those exponentials are supposed to get its base result. After getting the result of exponentials base of 2, all multiplied by 0 will remain 0, but the number 1 will getting the non-zero result and add all to get its decimal number. And next, a binary into octal. In grouping of binary digits into 3 numerals, in avoiding confusions or errors, it must be initiated in the right, like a calculator, to group a binary concisely, that in this example, there are 2 extra zeros in the first binaries to instill the count for groupings as 3 for octal. Now in here are binary into hexadecimal, in grouping a binary digits into 4 numerals. In according to number system table. In this example, octal to decimal. In the binary is listed upward reading. Even here in octal that listed upward. Then each numerals are multiplied by octal base 8 with increasing exponent. That 8 raised to 0 will get 1. And 8 raised to 1 is still 8. While 8 raised to 2 is getting 64. And after getting result, add all and now getting a value of octal decimal. Now in this example, octal to binary, in getting the binary of each decimal digit of octal to get each binary form, like in this table. Octal into hexadecimal are same as others, that octal in first column is written upward and multiplied by radix 8 in increasing exponents and getting the sum to add and to confirm it was decimal 74. And next, hexadecimal into decimal. In column 1, A has equivalent decimal 10, that 4 was a remainder.
and multiplied to radix 16 in hexadecimal. Next, hexadecimal into binary. In this example, a binary of 4 which is 100, but it is in hexadecimal form that has 4 base. So there must be additional 0, colored blue, and A or equivalent into 10 that has a decimal of 10, and binary is 1010 with the hexadecimal A. And last, hexadecimal into octal. In order to get the octal of hexadecimal, is needed the decimal result, then the octal has radix 8, then decimal 74 must divided by 8, and resulting its remainder into 112. Therefore, the octal of 4A is 112. That table is identical to hexadecimal to decimal in getting the octal. In conclusion, a main goal of computer organization and computer architecture is to reduce the execution time and to run a better performance that all integration, both software and hardware, runs efficiently. And that's all ends our module in Module 9 Computer Systems, Organization and Architecture. Thank you.